So, Dr. just from Institute. Sorry that there is some noise behind me. Still, I hope that I'm audible. So I'll just give a small introduction about what is this SIEAS and what we do. So basically, we do research and training courses. Previously, we conducted different courses, and you can get the details of the courses that we conducted previously in our website. So some of our upcoming programs are, one is there will be a data analysis course using R programming, and there will be, we are planning one course on Gaussian software, DFT calculations using Gaussian software, and courses on molecular communication. So this is one course, and not this reference management training, we did it previously, okay, and Monte Carlo simulation also we have done a couple of months ago. Now we are planning some electrochemical data analysis course in the future. So please do not mind the dates which is put in this slide, which were prepared previously, but we are still to conduct these courses. This is in fact in our plan. And we also give some research internship training opportunities. So this is something which we are planning for the future. So we are planning 3 to 6 months student projects, giving them mentoring. So basically the motivation is to help them to do some meaningful research and something like some publishable work for undergraduate students as well. So right now we are planning this online. So the mentoring will be online, and even undergraduate students can join us if they are research motivated. So there is a membership program with us that faculties and students can take a membership so that they can collaborate in our programs. They can be resource persons in our upcoming courses. They can design courses. So it's basically all about joining us. So once you're a member, you'll be more close towards, you can be part of more discussions. And also there will be some financial benefits when you join for our upcoming courses if you are a member. And we are also planning to sign MOUs with an academic industry. So like you can open a chapter of CR's Research Forum in your institute, and that will have some structural organization, like there should be at least one faculty member and 10 student members from your organization to start a chapter. So once there is a chapter, then we will be conducting programs together jointly with your institute. So that's another idea on that. And so basically this is the forum, this is what we do. And you can find more details in the website, and also you can email us to get more details. And I'm extremely sorry for the background noise. In fact, I'm sitting in my lab right now. So I'll just go to today's program. Today we are starting the first day of our quantum key distribution. We have Dr. Hashir Kunil with us. Hashir is a senior PhD researcher at Electrical and Electronics Engineering in Özyeğin University, Istanbul. So he obtained MSc Photonics from Manipal Institute of Technology, and his PhD work is towards the implementation of super resolution and high SNR quantum image systems. So Mr. Kuni is working in the scientific and technical research institution, Turkey's project that implements the first quantum key distribution network in the country. So basically, he is working on some cutting-edge research in quantum key distribution in Turkey. So he is an expert in this, and we are really privileged to have him with us today. So I invite Dr. Hashir Kunil to take over the platform and to start the course. Hashir, it's up to you.
Thank you for the nice introduction. Hello everyone, welcome to the program. So I will start sharing my PPT slides. Can all of you see my slide?
Yes, it's visible.
Okay, thank you. So this is the beginning of 10 days lecture series about quantum key distribution. So this is the first day of the lectures, and I'll be going through these topics during these 10 days. So I will start with talking about some introduction about quantum key distribution, where I will be talking about why we care about quantum key distribution. And basically, we want to implement physical system in this program. So I will introduce some optical components here in today's lecture. First, I will go through this optical components. Some of you may be familiar with these components, but since not all of you are not familiar with these components, it is very important to introduce here, and I will go through each components one by one. Then next day I will move on to basic quantum mechanics, where I will be talking about very important quantum phenomena. Those are superposition, entanglement, and then I will move on to talk about bracket notation. You may be seeing those notations during your previous time. And bond, modulus, square, expectation value, those things will be explained. And these parameters, those are very important for this quantum key distribution system. So, but when I talk about quantum mechanics, I don't go derive equations and all. For example, I don't derive Schrodinger equation. Those are not needed. I think for derivation, you can go through any books and all. It's very available everywhere. And no need also for this program. Then I will move on and talk about some Python libraries. These are very important libraries which we can use to implement the quantum system. And also this tool I have used to prepare experimental protocol for quantum key distribution. So for example, if you learn this code, you can basically prepare yourself and run the system, experimentally run your system. You will be able to do experimentally run the QKD system if everything okay. So next, I will introduce very important concept in quantum mechanics, that is single photons. That is very important for any quantum key distribution program. And then I will explain how to produce entangled photons. This is called the spontaneous parametric tone convection. That is the process I'll be discussing in 2 days, day 4 and day 5. I gave 2 days for this because this is very important. There are several ways to generate entangled photons. This is photon-based entangled source and discrete QKD system. There are continuous variable. You don't have to worry about that, but this is SPDC, that is spontaneous parametric tone conversion process, that will that is the system, that is the source we have for the entangled system. Basically, most of the people may be aware of a theoretical part of quantum physics, but they most unlikely they will not know how experimentally do such a system. So this is the solution for that. Then I will experimentally demonstrate quantum correlation. So here I say experimental demonstration. That's not a video demonstration, but I will sketch the experiment and I will discuss about the parameters of each component. And I will talk about what are the things you have to take care of and those things, and how do you experimentally implement the system. How do you in your lab, or like how can you be able to think about it? That is the idea here. Then I will move on to talk about the protocol, that is quantum key protocols. Those protocols are used when it comes to quantum system. For example, BB84 protocol, that is used unlike classical system, for quantum system, BB84 protocol. There are several protocols, by the way. So I will discuss BB84 protocol. That's very important protocol that can be used when you are dealing with quantum key distribution system. Then there is a CURD91 QKD protocol that is completely based on entangled photon source. So then I will talk how to how do you implement such a system in the Python code, and I will, if possible, I can share with you the code also if relevant, or we can use ourselves and we can do while in the program. We can do ourselves since you'll be familiar with some of the libraries of Python. We will be able to do the simulation for this. And then finally, I will experimentally demonstrate the CURD91 protocol that is based on quantum entanglement, principles of quantum entanglement that cannot be mimicked by any classical system. You need a quantum system. That's why we are using entangled source, that is basic fundamental quantum property. So I will move on and talk about cryptography. So what is cryptography? And by the way, if you have any questions, you can interrupt anytime. No need to wait for ending the ending the lecture. You can discuss anytime. You can interrupt me. There's no problem on that. So why cryptography? Cryptography is for securing communication in the presence of adversaries. If, say, for example, you wanna transfer some message, text message or any message, so it should be secure text. You don't want to reveal the text, like our OTP code. You don't want to reveal. There should not be a second party. They know this code. If they know this, it will drop your security of the system. It may be the security means it can be a big secure problem. For example, it may be some big banking transaction. It may be a password of your bank account. It can be even further bigger problem, like you have a military communication. If an external party interrupt the message communication, then there's a problem. There's a big risk there. So the cyber way, the modern way, that is cyber way, cryptography is used. So there are two types of cryptography: symmetric encryption cryptography system, and asymmetric encryption, also called public key distribution, mostly called RSA. Most of the time, most of the websites use RSA algorithm. And this is the crypto system. By the way, you follow my arrow, right? Sometimes I hear that people cannot follow the arrow. Can you follow my arrow here?
Yes, we can.
You can follow. Okay, thank you. So there are cryptanalysis, that is active and passive attacks. I won't be talking. These are a classical way of encrypting data. So I won't be talking mostly about this thing. I will be talking about quantum key distribution, quantum cryptography actually. So, but I'm giving the introduction how the security works. Why do we care about quantum key distribution? So, so most of the system, like I said, is working with RSA principle, that is asymmetric encryption. So maybe okay. So for example, what are the elements of encryption? For example, you have a message. This is your message. Then you use an encryption algorithm and encryption key. So these three, 1, 2, 3, you use to encrypt the data. So for example, you have a message that you make it into binary form. Say for example, you have a text, you make it into a binary form. then you have a key, encryption key, that is known by only you. There's no party knows that key. There's no one else, no unauthorized person has access for that key. Whoever has that key, they can access the message. So 1, 2, 3, these points will encrypt the data, which means that you have a message. Say, for example, hi, you make it into binary form and add the key. Then you have the encrypted key. I already did the encryption here. You can see this. This is done by me. This is an encrypted message. Okay, I'm not saying what is the message embedded in this. This is binary form of a message I embedded. So there's a key here. This is a key. It is a prime number that I converted into a binary form. Then I have access for this key. So I have the message now because this was encrypted by this key. Since I have the key, I can access this. This is done by 4, 5, 6. So encrypted message is given to you, and you use the key, the one you know, and you subtract it, you get the message. Only you know this. Let's see, I will go to program. I prepare this. So these are the two 5-bit text. This is a 5-bit text. I will let you know what is the text encrypted here. So I am going to the code. There's a code written here. So you can see this message here. See, I am copying this message. So this is the message I put there actually. So basically what I did was I have a message. So this is my message, QKD. QKD is my message. How I prepared the QKD, this text I converted into binary. You follow the code, right? You can see my code. I hope so.
Oh, it is not visible clearly. Can you just increase the font?
You see now, do you?
Yeah. Yes, now it is.
Okay. So this is my, I want to send this message. This is QKD. So I have this converted into binary form. This is 5-bit code. For example, A stands for 0000. 50 stands for A. 00001 stands for B. Maybe I can show that here. Just a minute. Okay, here you can follow. So A is for 00001. Okay, B stands for 00010. It goes like that. So if I want QKD, so I converted into Q is for 1301, K is for 01011, D is for 00100. So I converted that into binary form. This is all put together actually, QKD. So this is a prime number. I will come to the point why we use prime number here. And then I used this thing and I add it together. Then I run the code. So I get this one. See, this is the one. This is the message. I have encrypted message. Now this is encrypted message actually. So you can see that this is the encrypted message here. So if a person who doesn't have the key, they cannot subtract. For example, here I use the encrypted data. So I have the encrypted data here. This is encrypted data. So I gave encrypted data. I am subtracting the key. This is the receiver side, for example. And I will subtract the key. This is the key actually, known by only you and me. And I will use this key and So this is the number. This is the key. In this program, I am subtracting actually. In the first program, I was adding. So this is the result. So you have the decrypted the code. Now you know from this I have put a QKD some from that. So this is how this system works. So so this is what encryption means. This key is known by only you. So you should keep it as secret. Nobody should know this. And there's another term we often use, that is eavesdropper. That is an intruder, external party that try to attack our key and get our key, which we want to keep it a secret. So that is a word we'll use for eavesdropper. Sometimes we call Eve. So let's come to symmetric crypto. In symmetric cryptography, encryption and decryption are done by using the same key. So this is a very fast way. So for example, we share the key by physical ways. For example, I have an envelope, it carries a key. So I want to share with someone, I will physically carry the envelope and go to that person, intended person, and give him the key. So he and me has the key. This is a bit primitive way. And so we will use the same key and do the process and get the message out of it. That's how it works. So here the security is beared by the fact that we will keep it as secret. And secondly, randomness. We keep the secret key as random as possible. We don't so that nobody should guess your key. Then comes to asymmetric crypto system. So in asymmetric system, crypto system, it is done by using different keys, and they change the keys often actually. And here the point, this is very important point. Most of the websites, most of the secret currently secured by this system. But how this system is secure? The system is secure by computing difficulty of mathematical problem for the key. So if I have a key, so if there is a eavesdropper, he comes and try an algorithm and try all the possible iteration and get my keys out. They can do that, by the way. The only problem here is that the computing and finding the key will take years, 2000 years. They cannot, an eavesdropper cannot wait 2000 years to get the key. So this is how this is secure. There are mathematical problems that cannot, the computer cannot solve. The present day computer cannot solve that efficiently, fastly. So that is where the security is done here. So here so I will go to next slide. Why we talk about this and what is the problem here? So we have everything secure now, by the way. At present time, there's no problem. In fact, your crypto system, classical crypto system, works well, fine, no problem. So why do you care about quantum key distribution? So the problem is when the quantum computer come into existence. So there's an algorithm called Shor's algorithm that can solve this problem very efficiently. The RSA problem, the asymmetric key sharing problem, can be solved by using quantum computer when it comes into existence. So that is the problem in future actually. So, but many national security agencies care about this a lot. Personally, you can hear a lot of news about quantum computer getting improved, and there are predictions that by 2029 there will be a quantum computer that can solve these mathematical difficult problems. It includes RSA algorithms, the security generated by the RSA algorithm. So this is a threat to the national security. It is a threat to the any communication that kept to be secret. So, but I'll say that symmetric algorithms are still safe, but still there is a security delivery and the randomness of the key problem exists. But only solution for this is that quantum key distribution that nobody can solve, because the principle the QKD works with is by its nature. It's not like a mathematical problem that takes long time to solve. Rather, it is a physical difficult. Nobody can solve, even doesn't matter how long they run the problem, because this is completely random. Nobody can predict, even computer cannot predict what will be the state of the system that we will see while discussing about the program. So what is the Shor's algorithm, and what does this do? Basically, I was talking about RSA algorithm. So RSA algorithm. So let me go to some website how they're secured. You can also access, anybody can access the secure key and see how the system is protected. You can actually see, anybody can see. So for example, I will go to IIT Bombay website. Since all of you know IIT Bombay, I'm just randomly taking this. So go to this here. This is encrypted data. So go here and you can learn more about this. Sorry. Okay. So you see here, this is issued by DigiCert TCL RSA. So this is protected by RSA algorithm. So you can see the details here. So see, this is protected by RSA algorithm. You can access this key, by the way. This is public key. The key, the message I showed you, it is the public key. And this is public key parameter, and this public key is protected by using a the public key. Actually, it is encrypted. This is not message itself. This is the message plus the key added. So from this you have to extract the key. So this is a very long number. This is 2048 bits number. And there is E parameter. Actually, you don't have to worry about that. So this is the situation here now. So let me come to the slide. So here, see, okay, it is protected only when the digits are very long. Actually, if it is short digits, it's not secure. Anybody can solve. In fact, any one of you can solve, no problem. So how it is difficult mathematically? Say you have a number, the number n here, that is the number you saw in the IIT Bombay website. So that is the number here you have. How they generate the number? They multiply two prime numbers. 3 and 7 are prime number, you get 21. 13 and 17 are prime numbers. If you multiply both, you get 221. These are prime numbers, but if you use these prime numbers, I can solve the problem. I can know what is the n value. Let me go to my code and show you how it will be. I have a code prepared for you. So this is prime factorization program. So here, so enter a number for calculating prime factors. For example, let me take a small number. 91. 91 is a prime number. Sorry, 91 is not a prime number. So I want a prime factorization, by the way. So 7 and 13. These are the prime numbers that multiplies, you get 91. Let me use another prime numbers I have prepared beforehand. Say, for example, this one. Let me see. So this is a prime number. Since it's a prime number, you have only one number. There's no other number multiplies. So this can be solved. If you use this big prime number, it can be solved. There's no problem actually. Let's use a little bigger prime number. Let's use this prime number. That's not a prime number, sorry. But see, it is very fast. And go to a prime number here. This is a big prime number. Let me try to solve this. See, this is a solved. See, but it took some time, by the way. See, this is the first. You follow here. If it is red mark, the system is running, still running. But if it is not red, sorry, not red, black dot, if it become black, it means system is running. Okay. So if I put that number, you can see that. See, I ran. Yeah, it took this much time to run this, find out this prime number actually. So let's go to a little bigger prime number. Let me go to this one. This is also prime number. No need to take one, by the way. I prefer that way. So if I take this one, let me see how much it takes. So you can see this has solved. Even this big prime number is solved. Let me take another one that is very big one. Let me see. You follow here. So this is running. The system is running. Now solve. Let me go to another bigger than that. That is combined of two. Sorry, this is the number actually. This is the combination of two prime numbers. And we need to get the prime factor for this. So the system in this case, you can see that it runs. I didn't use very long. It can also solve actually by time. Maybe, I don't know actually. I didn't wait. I didn't have patience to wait until it solved. But see here, follow this. You cannot prime factor this that efficiently, that fast. This, I am using a classical computer, so it cannot solve such a problem. So RSA algorithm is protected by this kind of technique. So this is not about, this is about time taken for the computation that secure your system rather than the system generating some other form. So system is still running here. You can follow here. See, this is running. So since it's going on, keep on going on, I am just interrupting this and stopping the program. So I interrupted and stopped the program. So let's move on. So, okay. So
hello.
that's the thing.
I have a question. Is there a reason why the factor should be prime?
Hello.
Is there any particular reason why the factors should be prime?
I cannot hear you properly. What did you ask?
Is
There
there
is
any
an introduction.
is there any particular reason why the factors that, suppose in the first example, 21 is equal to 3 times 7. So is there any reason why all the factors should be prime?
No. There's no reason like that. Just you can take the only point is that the in IIT Mumbai website I showed, and it can be any prime number, but it should be very large.
No, my question is why prime?
Why?
Suppose my number is 4, and instead of taking 2 times 2, what if I took 4 times 1?
No, one you like prime number, you can divide itself and 1. So you cannot take 1 as a prime number. You cannot know that actually. Even if any prime number, you don't have to. In fact, not only factorization actually. If you take any big prime number itself, okay, just take very big prime number and try to factorize. Try to find that prime number if it is prime or not. Try to find if it is prime or not. Even you cannot do that.
Okay.
So yeah, it is not just this. The main key is okay. Of course, you cannot factor this if you have a very big number created by very big prime numbers. It is protected itself, but the basic from this basic coming from the fact that the prime number itself, you cannot know prime number directly. If you want to find one is a prime number, you need to go through several iterations. Then only you can find if it is a prime or not. Instead of using, if I use a very big prime number, you cannot know if it is a prime or not by algorithm actually. It's very difficult. You cannot know like the prime number or not. That itself is protected.
Okay, but being a prime number or not, or this prime factorization, how is that related to encryption actually?
Okay, so oh, okay, you are saying that how this factorization is related
relevant to, yes.
Okay, I see. So you have a message, okay? You have a message like I previously showed.
Yes, the message we encrypt with an encryption key, and then we decode.
The key is the secure key. So this key, if you wanna know this key, this is a prime number. So you have to look which prime number this is. So you have to go through, take an algorithm that try to find if it what is that key, possible key. So you have to find one prime number and put it there and see. You have to follow that procedure one by one, and finally arrive at the key value. So once you arrive at the key value, you cannot do by classical means, by the way. So once you as an Eve, you as an external party try to gather that secret key, cannot do that because you don't know that number. If you want to know that number, what you have to do is that you have to prepare an algorithm that try to like you have a lock, number lock. Like you try all the numbers, and finally you arrive at a point and you can open. Likewise, this key, you prepare an algorithm and do all the possible values and see which one is that. So that's where the prime number come into the point actually. So that's how
encryption key that you showed is a binary number, right? So you're saying that binary number represents a prime number.
Yeah, that's true. Yeah. This one actually, this is a simple example. This one I used a small prime number, by the way. This is a small prime number that I converted into binary from the prime number 2. I converted just to binary number. That's it.
Mm-hmm.
I can just show that. For example, let me see. See, you have see, I have a code. This is the number, by the way. This is the prime number. Okay.
Mm-hmm.
I used this prime number and generated the key binary form. So now this is your key. That is what I used, by the way. But I used a small just to demonstrate. If I in actual case, you have to use very long. In fact, it will be like 2000 bit data. So
Okay.
for just for the demonstration, I used a small one. Mine is of course not protected in that way.
But then
Yeah,
one can have binary to decimal conversion. So that you're saying will take a long time for a classical computer to do?
No, not that. Okay. Like to find out the secret key. Classical.
Okay, how is secret? That's the question.
Yeah, yes. Conversion is very easy. No problem.
Yeah.
Like I can like just copy any
Yeah.
big string. We can easily do that. No problem. But to find out what is the number, like as an example, I'm giving that you have number lock. Then you have to like say for example, you forgot your numbers. Then what you can possibly do, if it is 3 numbers, you have to go for all the permutation combinations, right? Then finally you arrive at a point that you can open. You got the key actually. Likewise here, for prime number protected RSS system, you have to get the an algorithm that runs very fast and solve it for you and get the secret key. So that's how we can do that.
Okay, but the algorithm that you showed, it is just given a number, it is trying to find the prime factors.
Yes,
right?
yes.
So how
correct.
is that related to finding a secret key, the encryption key? Like how is that related?
That is not related actually. I'm just showing that this is difficult to do. Here I'm just showing that it is difficult to make a prime factorization. But
Okay.
I am not showing the actual algorithm that if an intruder can use and solve for the key. I'm not using that. But this is how it is protected. That's what I mean.
Okay.
But that is actually easy to like get such an algorithm that is available, by the way.
Yes.
But the problem is, only problem here is not algorithm itself. It's the problem is that the computer cannot solve this in time. Actually, it takes long time. That is the problem for the intruder, problem for the thieves.
Okay. So what kind of algorithm any hacker would use to find out the encryption key for the communication? So what kind of algorithms are those?
Now they can presently there's no algorithm that can solve.
Okay.
There's no algorithm, but when a quantum system comes into existence, that is called Shor's algorithm. That can be used to solve this kind of problem, because quantum system that's work with the principle of superposition state. So you will have all the states together in many number of states together, and instead of solving for prime number one by one, you will do all together, so that the I don't know how many zeros are there. This much years taking classical computation taking this many years to solve such a problem. For quantum computer, by using Shor's algorithm, I won't go to Shor's algorithm. That's a quantum computer problem, by the way. So if you follow that, you can by 100 seconds you can solve such a problem. So that is the problem, and that's what that's why the people care about quantum key distribution, quantum network. And presently we are predicting that in near future, in a decade or 2 decades, quantum computer will come into existence, and most of the governments are preparing for this problem coming into existence in future. So that's why QKD is very important. And this is now I will move on to the most important part. This is needed for understanding the quantum physics and how QKD system is run, and especially when we talk about the experimental scheme and how experimentally you do, or how do you do by using Python code, and how to check, how to calculate. For these things, these optical components, these are basic optical components. If I miss something, I will later come on and discuss about that. But these are very basic optical components needed to learn about this system. Most of you may be familiar with these components, I think so. But some of the components, I think, even though you know, you may not have first-hand experience. Otherwise, I think most of the people know this thing. But still, I will go through it one by one. So hereafter, I may use my pen also to write, and that is more convenient for everyone to follow. I feel that if that is not convenient, I may change that plan in later lectures and put pictures and do that. So laser, that's very important component. We cannot use LED to demonstrate a QKD system, as far as I know. We need a laser as a source to demonstrate experimental QKD system. So what is laser? Light amplification by
stimulated emission of radiation.
There is some problem, just a minute. Sorry, my mouse is not working. Okay, started working. So this is amplified light, and it is stimulated process, and a light wave is emitted by the process of energy exchange. So you have the laser. These are the three. There are two more parameters I will be discussing. The first one, most obvious one, is that it is highly directional because it is stimulated emission. So you have a laser medium, and if you give a external energy, and if it is laser, your light is more directional. I will show this way. It's more directional. Suppose you are using an LED, the problem or spontaneous emission in that matter. If that is the case, you have 4 pi emission, you have all the direction emissions and all. And one of the things, when I do experimentally, I noticed that the more important thing is that when you use an LED, this is an LED, say for example, your light will be like, say, going this way, this way, this way, all the directions. Say then, when you use a lens, sorry for the drawing. So you can see that the light won't go straight like this. Instead, light, if you put another beam, another lens, your light will focus straightly for laser. But if you're using an LED, it most likely you will like have many focal points, and it has all the directions. So for laser, it is more perfect. It will be, if it is monochromatic, by the way, there are other classical factors like aberrations, and there are several problems. Classical, it cannot focus straightly. Say, for example, if you're using many wavelength light, it can focus several locations, and This is because of a spectral property of light source. But if you're using a single light source, it will focus strictly on here. But still, let me confirm you that it is still not like single point. It has it is distributed here. Again, that is also a quantum phenomena. Most of us may miss out that point actually. But this is the laser light. This is highly directional, and your beam will be directional. It is called collimated light. This is mostly going very parallel. Light will be going very parallel to each other. So this is collimated light. So second point is that the light is monochromatic, which means that if you use a sunlight, that is and that's not a laser light, that has all the wavelength, most of the wavelength. You have ultraviolet, you have visible, most of the visible region, you have infrared, all the light you have. But laser, when you say laser itself, say for example, when I say laser of wavelength 780, which means that laser with 780, if you use a spectrum, this is wavelength, you have a 780 nanometer peak, and its distribution is very narrow. So you don't have this is of order of 2 nanosecond, 2 nanometer, 3 nanometer, 10 nanometer, something like that. But if you're using a LED, this is very broad mostly. So this is not monochromatic. It is this is monochromatic. This is not monochromatic. This is this multi-chromatic light. So laser is a monochromatic, which means that it gives single frequencies, even though it has some distribution. By the way, it's not strictly single. When I say about 780, it doesn't mean exactly 780. There's no 780 plus or minus some value. Usually, it is plus or minus 10 nanometers value. And also, another point is that laser light is highly polarized, which means that if you take a light and look at the its wave, it will be like this. Let me show you. This is vertical axis. This is horizontal axis. So the light is parallel to the light vibration. The vibration of the light wave is parallel to vertical. So it is specific state of polarization. It can be vertical alone. It can be diagonal. It can be horizontal also, like this. It can be horizontal, it can be. So this is mostly polarized light, mostly polarized. I would say still there are some part of plus or minus. Again, here is not strictly. And if you take, but by the way, if you can make LED also polarized, there's no problem in that. But I'm saying the laser is mostly polarized light. Go to next point. This is very important point here, and it is unlike previous points, it's a bit difficult to follow. So this is highly coherent source. What does it mean, coherent source? If you like, if I take a wave, laser wave, it will be going like this frequency, this wavelength, sorry, this is lambda. This is mostly same over far distances. But if you go very far distance, it will be changed. This frequency will be bit changed. So how can I explain that? Okay, let me say, so maybe another light will start like this is x, this is displacement, x-axis is displacement, this is the amplitude, and you can see that this is this much distance, that is, we call it coherent length. It is following the same frequency, but after that point, it messes up. And this figure here, you look here in this region, it's mostly same frequency, but in this region you have less. So you say this in this figure, coherent length, this one. This coherent length is very high for laser. So if you take sunlight, the coherent length, so for 800 nanometer itself, sunlight the frequency become expanded or compressed, or it is completely problematic. And if you take LED, that is also, the coherence length is not that long. It is 20 micrometer. Some of you may be familiar with the Michelson interferometer and all. You can see that if you use sunlight, getting a fringe pattern in the Michelson interferometer is a bit difficult. But if you go to LED, you can get, but still it will be difficult. And if you go to sodium lamp, it is 600 micrometer. And for laser, it is 20 centimeter. I don't know if you see. Okay. So if you look at the single mode helium neon laser,
you can hide that. You can click on the hide and it will disappear.
Okay, thanks. Okay, single mode helium neon laser. If you're using single mode helium neon laser, it has 300 meter the coherent length. So if you have a Michelson interferometer, those of you know Michelson interferometer, you can have two mirrors. Difference can be 300 meters, still you will get a fringe pattern. But even though you don't know the Michelson interferometer, don't worry about that. You don't have to know also. But this is the scenario. Your coherence, it is highly coherent source laser in that sense. And this is, I'm showing non-coherent light here. This is for LED. I simulated it, by the way. So you can see that it is completely random. So that makes some problem. And that parameter is very important for our purpose. So another very important property of laser is that high intensity. The intensity of laser is very high compared to other. This is the very famous parameter. Most of them, you know. So highly directional, high intensity, high coherent, and polarized single polarization single state of polarization. These parameters makes laser very unique. After the inception of laser, the physics experiment became very easy. There are many quantum experiments that were not possible before the existence of laser could be able to do in the present time because of laser. And for me, if I want to do the research, I need the laser. Without laser, I cannot do any quantum experiments. And so about the intensity, so what happens here? So here you have the medium that have lacing medium, we call. So you give external pump. When you give external pump, your particle energy go to excited state. Since it's not very, I am not going in depth into this problem either. So if you give energy, pump energy, there are particles that will go to excited energy state. It can be in vibration mode. Vibration will become very high. Can be other way also, by the way. So when it comes back to release the energy, it emits photon. If you don't give external pump again, it will randomly emit the photons. It will go from excited state. It will come back to the ground state. So while coming back to ground state, it generates some energy, some photons, by the way. So that is called spontaneous emission. That is completely random, like I previously noted. But if you give pump again, then you have simulated emission. That's what laser stands for. So simulated means it's highly directional. What happens? Your excited atom will collide with another atom that's in ground state, which will create same frequency, and this process will move on. And finally, this is inside a cavity, and it can exist only specific. Only certain frequencies can exist in the cavity because of, again, quantum mechanical reason. So finally, it will align in this fashion, and when it is reached at some saturation, experimentally it's a bit difficult, by the way, and there are some parameters we have to consider. That's why not anybody can generate prepare laser, by the way. So finally, it will leak out some energy that is called highly directional, highly coherent, and state of polarization is single and monochromatic. This parameter of laser is very useful for our research. And so I will move on to the next parameter, that is polarization. I already have explained that. If light wave propagating in all lateral direction, it is called non-polarized light. The figure you see here, it is polarized light. But if you have horizontal component also, this is called, so this is vertical one, say I call vertical for this axis, horizontal for this axis. And if you have this all components, by the way, not only vertical and horizontal, you have all the components, and then you have non-polarized light. If you have only single component, it is called the polarized light. And for vertically vibrating like this, we call it vertically polarized. Throughout this lecture series, I will follow this terminology. I will call it vertical, not S or P polarized. In quantum physics experiment, most of the people use vertical or V or H notation for easy of following. Most of the book, in fact, I didn't see any other notation, by the way. H and V, they follow H and V. So you can follow H and V for this course through it. I don't use S or P. And so this is the light, unpolarized light, okay? So unpolarized light, and I'm talking about linear polarizer now. So what does a linear polarizer do? Linear polarizer selects only light wave vibrate parallel to polarizer axis. For example, this is a polarizer. You have a polarizer. This is an optical component that will allow the wave vibrating parallel to this axis, because this window is aligned with that. So it will allow only that wave to pass, and it will cut off all other wavelength. For example, this one will be cut off, this will be cut off, all will be cut off. And if you come to here, and I want to point out this, that here, say for example, you have the light has an intensity I. If you come after the linear polarizer, it will be still I. There won't be any change in intensity by means of blocking. There must be some reduction because of optical component will absorb some light photons. So otherwise, this process won't reduce the intensity if you shoot the unpolarized light to the polarizer, and you will see a polarized light as an output. So, but polarized light has only single vibration, and this is vertical in this case. And say for example, on the other hand, if you're using a polarized light and put a linear polarizer. This is called linear polarizer, by the way. So, but this as axis parallel to the perpendicular to the vibration of the polarization, which means it will cut off all the intensity. Sorry, I will connect power. I will charge my laptop first. Sorry for the interruption. So, okay, if you are sending a polarized light, say you have a vertically polarized light. If you're sending a vertically polarized light, then if you're putting a linear polarizer, that axis is parallel to the send light. So you follow this definition. This will not cut off any frequency, because cos 0, the angle between the vibration of polarization and the linear polarizer is parallel, which is 0. So cos square 0 is I. So I is the I0 is the input power, I is the output power. So output power, output intensity will be same before and after the process. But in this case here, here you're using a cross alignment, which means that your light is vertically polarized and your optical linear component is orthogonal to each other. So which means that theta become 90 degree. So what happens? It will cut off all the wavelength. So if you have any questions or something on until now, you can ask or just skip. I think you most likely know most of the, but okay. So, and let me come to light models. There are light models. When we talk about light, we sometimes talk polarization, sometimes we say wave, and sometimes we say light is wave, sometimes we say quanta. Basically, light follows all these properties. Light shows all these properties. Light you can consider as a rays. Say, for example, you have a camera. Let's just. You have a camera here. You have an object here. So there is a pinhole here. So you put a lamp like this, and you can see that only ray go through this way. Other rays all blocked. Other rays are blocked. So the top one will go like this and hit here, and bottom one will go like this and hit here. So it will be inverted. And if you put a camera, you will get an image of it. Likewise, say you are sending a stream of light and you have some object blocking it. Say this is a pin. This is a pin blocking it. So you will get, when you look from the front, this is front view of this light, you will get this part cut off. Only light will be passing through that. This is kind of a ray model actually. So there is another model. This is scalar waves. Light we consider as a wave phenomena. So what happened, like we see in the ocean, say you are sending one light here and another light, okay, one monochromatic light here, and that sends light through both slits. There are two slits. And if light at the middle of the point, sorry, here, this point actually, intensity will be maximum because you have a wave, one wave like this, other wave also parallel to each other. So amplitude will add up here. So here you have maximum intensity. So you see when you put a camera here, the maximum intensity. If you go a little off, so what happens? This is shifted. So in that case, the scenario will be a bit different. In that case, here it will be like this. So lights are cancelled out in that point. So you will get minimum in this point, and it continues that phase. You call it phase actually. Phase shift is here in this case pi by 2. Sorry, 2 pi phase shift, which means lambda by 2 phase shift. So in this case, you get minimum, maximum. It follows a fringe pattern, and finally you will get an interference pattern. This is scalar wave interpretation of light, and so basically, I want to point out that if you consider light as a photon, then also you will get this, but that is a bit different topic. I will talk in that context later on. So we can also describe light as a polarized light, and we can discuss about it. It is like I explained before, we can consider light is polarized light, and if we will discuss more about this thing later on. Again, this vector waves and quanta we will discuss most of the time. We won't discuss scalar waves, ray optics much, but I'm just pointing out these points. And another point is that is the one we are mostly interested in. So where you consider light as wave packet, which is called quanta. So in that case, we consider light as a particle. So if you take a light and look at inside as a particle, you can see that this is photon. I'm representing photon like this. You can see lot of photons bundled together. That is the light. You can consider light as this also. And this is originated by when everyone failed to explain some of the physical phenomena. Those are photoelectric effect, black body radiation, and Compton effect. How this actually happened. When in that thought, Einstein finally pointed out that light is also a particle that follows particle behavior, and he called it quantized. So the energy of each wave packet is h bar omega. This is energy of each wave packet is h bar omega. And because of quantum mechanical descriptive nature, energy is written n h bar omega. N is integers. It can take 1, 2, 3. It cannot take 0, by the way. The minimum energy is 1. So any system which has minimum energy h bar omega. Later on, maybe we will discuss that it has a vacuum energy state. It cannot have 0. So anytime you have some vacuum fluctuation, and it has energy, some energy. So it can also written as hf. Hf is the frequency of the light. H is the Planck's constant. So let me come to another two important optical components. This seems very simple components, but it is actually extremely important optical component. You have a beam splitter. Beam splitter, as its name stands for, you have a light beam. Light comes. some part will be transmitted, some part will be reflected. Some part will be transmitted, some amount will be reflected. What is very special in this is that in our, especially in our experiments, here we are talking about rays. So you have one ray coming and some amount is transmitted, some amount is reflected. So say for example, I am using 50 beam splitter, which means that if you put high intensity light, you have I/2 intensity at the transmitted arm, you have I/2 at the reflected arm. But let me ask you one question. What will happen if you use single photon? I was saying that light is also a light is also following a particle behavior. If you have a beam splitter, I simplify it as BS, and light photon comes here, what will happen? Can any of you tell that where it will go? Can you say
half probability to see in both places?
It has 50% chance to go in either of the directions.
Yes, yeah, 50% of the chance. But let me ask you one more thing. Can you predict that in which arm it will go beforehand? We cannot know that beforehand, right?
No.
Yeah, that is the randomness in quantum mechanics. That is what single photon is very important. We cannot predict beforehand where it will end up. It will be transmitted or reflected. Nobody can say. So, so this is some of the randomness. This is one of the very important parameter. It seems very simple, but very important. But creating a single photon is very tedious job again. But if you have a single photon source, it is very difficult. Not very difficult. It's impossible to predict where the photon will end up, whether at the transmitted arm or it is at the reflected arm. So this is one of the parameters used in quantum key distribution as a tool to protect the cyber system. And again, this is also very important component for quantum optics. So you have PBS. What is PBS? Polarizing beam splitter. Say for example, you have a light beam. This is vertical. This is diagonal, I would say. D, I will say D. Diagonal component. Say you send diagonal component of light. What happened is that 50% of what happens is that 50% of the light intensity will be transmitted as horizontally polarized, which means that all horizontal components will be transmitted and vertical components will be reflected. Say if I send a light that is vertically oriented, if you're sending only vertically polarized light, what happens? You won't have this. You don't have horizontally polarized. You have only vertical components because there's no horizontal components. If you send only horizontal component, then you have only horizontal component. There's no vertical component in that case. So then again, let me ask you again question. If you send a single photon that is diagonally polarized, you have a PBS, you have a light that is diagonally, say for example 45 degree polarized. which has, of course, horizontal and vertical components. What will happen to light, that single light, single photon? Same way like BS, we don't know. We don't know if it is horizontal or vertical beforehand. This scenario, we will write like this. Say, for example, you might have noted this notation several times, and it may be easy to follow, I hope. Horizontal, I will write like this. Vertical, say your light is say some angle polarized. Say diagonal, C diagonal. So you have an equal, or like this, how much it bended, because as per how much theta is there, like cos theta here, by the way, here sin theta. In probability, it is cos square and sin square for y-axis. So so it is again probability, but I'm not going to talk about that. I just mentioned here, you cannot take like this. This will come to later lectures. So if this is 45 degree, if you're sending a single photon, 50% of the time it can end up here. If it is single photon, you don't know beforehand if it is horizontally or vertical. This is again goes to the chance. So
can I ask a question, please?
Yes, sure.
Okay, so if I understand it correctly, the analogy between intensity and intensity is the number of photons. So how do you define polarization of a single photon?
I see. Intensity, number of photon is proportional to intensity. You have 1 milliwatt power, then which means you have, say you have energy equation, E is equal to n h bar omega, you know frequency, you know h bar, you can calculate the number of photons by that means. Let me give you some numbers, by the way. If you have 1 milliwatt of intensity light, it is 10 to the power 12 trillions of photons. Okay, when we talk about single photon, you should have in your mind that you cannot observe that by your eye. And let me say this also, I have dealt with femtowatt light power. So femtowatt, that's more. So light intensity you reduce, you cannot see, even though it is in visible region, you cannot follow that single photon. You need some amount of photons to follow your to detect by your eye. So this is the for your question, this is answer, this is proportional. But when you think about single photon, forget about intensity, because this is non-pay matter, because it's in very small unit. And also single photon means it has an energy of this much, and it follows this random nature, and we don't know where we'll end up beforehand. And let me say one more thing here. When you put a beam splitter, in quantum mechanics, we say measurement. Here, the measurement is here now. Say, for example, before this, you didn't measure the quantum system. After this point, you measured it, because it is decided already. It is just a factor of you didn't detect or you detected. So, next point, half-wave plate. I think I don't have to. I don't know if I can follow, take some time, or should I stop here? It is up to you, actually. We are reaching 7 o'clock. If you have some other business, I can stop actually and proceed next day. If it is okay, I can continue this lecture and finish and go. What do you say? Anything I should?
You can finish it.
What should I do?
We can
Finish
Continue.
it off. Continue.
Okay. Thank you so much. So maybe I can stop after this. I think it will take. Maybe I can do one thing. This is simple points. I can just show you one video, and it shows the photon numbers. It can give you some feeling that is experimental result. So let me play this for you. Let me tell that this is a timestamp unit. I will talk a bit about that tomorrow. It won't take much time, but let me wind up by explaining this point. See, you can see this channel 1, singles 1, singles 2. So there I have used 2 detectors, single photon detectors, that is connected to a register. So that register gives how many photons you observed here in by one detector and by another detector, this one. So these are the number. This is we are following the light. We are modeling the light as a particle, and we are counting how many number of photons we are detecting here. So since I talk about photon numbers, usually in most of the scenarios we deal with wave and how its interference and how it behaves in double slit experiments, something like that. But here we record numbers, light as numbers. When you have a detector and detector sensor is received by light is sensor receives the light, it will count how many photons it received. Okay, I think I can find a. I don't know. Some of you maybe wanted to leave, and so I can talk a bit about this tomorrow. I hope you enjoy the lecture. And any question now? I think you can ask now any question. No problem about taking time for questions. Actually,
See, I have a doubt. Apart from prime numbers, what are the other keys we can use it for protection?
Okay, you are asking from previous slides, right?
Yeah. We have used a prime number as the key. Can we use something else instead of prime numbers?
Yes. For example, here this in RSA algorithm they use prime number. This is ECC algorithm. Let me go to my Gmail and look here. This is also encrypted. You follow this. Most of them I see as most of the time I see RSA algorithm, but this is different algorithm. This is ECC algorithm. And also you follow this 256 bits. This is much lower compared to RSA algorithm. What is it is that this follows some pattern, difficult pattern that is generated by some random number generator, if I am not wrong. But I'm not completely sure about that. But there are some algorithms, they follow patterns that is difficult to obtain by nature of randomness, I feel. So, but most of them are protected by RSA. If you go to any website, you will look at their thing. And if you can break this RSA code, you will be awarded very prestigious awards. Actually, it's that difficult. It's very difficult. Anybody has question, you can ask now about experiment or components. This also okay.
Okay.
Yes.
When it comes to lasers, using lasers for QKD application, so what kind of lasers do we use? Because like you discuss some of the properties, but it also depends on how one designs the cavity, and there are so many factors can tune in.
Yes.
Get refined properties.
You can design accordingly. By the way, you can use. For example, for me, I use QKD system. I externally demonstrated. We used coherent light. We used 405 nanometer central wavelength Ondax laser, which has bandwidth. How much it is? 10 to the power 160 megahertz. 160, not 160 megahertz coherence time. And its intensity is not very important for our experiment. Like our power maximum is 40 milliwatt. But if you wanna send to far distances in space communication, in free space communication, then you have to use high power laser. You have to go for high. You have to increase the power and reach the distance accordingly. But let me say this: this is long before our important lectures starting. We don't use laser as a quantum source itself. Okay, we generate quantum source. Laser is not quantum source, by the way. When you make it single photon, you can call it quantum source, but otherwise laser itself is not a quantum source. So, but we use laser, not LED, as a pump source to generate quantum source, by the way. You will see later that we will use crystal, some nonlinear crystal to produce such a system. But with laser, there are flexibility. You can use various kind of lasers. Depends on later on also you will see that various wavelengths also you can choose. When you choose wavelengths, you have to follow some parameters. So I think I will talk about that later. But this is a scenario. It is not very important. Any laser will do. Continuous wave laser will do. You can use pulse laser also, by the way. Yeah.
Okay.
Okay, then I think we can stop. I don't know where is the link. Do you follow me?
Yes.
Yeah, I don't know what happened. Like I don't see how to. Okay, I think we can stop today's lecture.
Yeah, I think if the host will stop the meeting, then everybody will get removed from the meeting.
Okay. I stopped presenting. You can leave the meeting, I guess.